Jai Hind, welcome to the course Network Analysis and Synthesis. Today I am going to discuss about the methods or techniques to carry out the network synthesis. We know that what is network synthesis? Network synthesis deals with the problem of design and fabrication of network when input and output are known. So, here if the function is given, if the transfer function or network function is given and you require to decompose this function to get the required network. So, how we will do it, that I am going to discuss today. So, basically this is the network function of any network. Okay. Now, you have to decompose this function to get the required network. So, what are the techniques and what are the methods by which we decompose this network function? So, basically there are four methods. So, removal of pole at infinity, removal pole at origin, removal of conjugate imaginary poles and removal of a constant. So, these four methods or their combinations are being used to decompose a given function. So, we will take one by one. When we remove the pole at infinity, when we will remove the pole at origin, when we remove the conjugate imaginary poles and when constant. So, this techniques in detail I am going to discuss today. So, when we carry out the first removal of pole at infinity, when we do it. So, when the pole at infinity means when the m is greater than n. When m is degree of numerator polynomial is greater than degree of numerator polynomial, then there is a pole at infinity. So, if Fs has pole at infinity, that is difference of m minus n is 1, it means there is one pole at the infinity. Okay. So, what we will do? We just divide the numerator polynomial by the denominator polynomial straight way. So, once we divide the numerator polynomial by the denominator, we get this term Hs, Ns, it is not Ns, it is n dash s upon d. We get this. So, when we divide the numerator by the denominator, we get this component, this element plus remaining functions. We have to carry out the division one time. Okay. Get one term, then check whether the degree of the numerator polynomial is lower or higher or equal to the denominator polynomial. Once we achieve this, when the numerator polynomial is lower than the denominator polynomial, then we stop there. Then we stop here. So, we get one element which is Hs, and Hs is nothing but it is Bm upon An. This is Bm upon An. This is your Bm and this is your An. So, when we take one division, we get this element plus remaining polynomial. So, suppose this network function is impedance. This Fs is, if Fs is Zs, it means this Hs is also Hs is impedance. So, it is. So, we know that if we take the XL is equal to j omega L, or we can write SL. So, this is impedance. So, this is a inductor. This is inductor of inductance H Henry. Okay. So, if Fs is Zs means impedance function, Zs means impedance function, So first element we get the inductor. So when the numerator polynomial is greater than the denominator polynomial, it means there is a pole at infinity. Carrying out the division, we get one element which is inductor if the function is impedance. Suppose if Fs is admittance, it means Hs is admittance function. So we know that if Xc is equal to 1 by Sc, so Sc is admittance. So if the Fs is admittance function, then we get one capacitor of capacitance Bm upon An. So depending upon the function, whether it is impedance or admittance, we remove one inductor or one capacitor by removing one pole at infinity. So this we can, so if it is impedance function already explained, so this is the impedance and it is a inductor of inductance, this value. So this is the, so when we remove one pole at infinity, we get one element inductor if the function is impedance. If the function is admittance, then we get one capacitor. So if the function is admittance, then we get one capacitor. So what does it mean? It means if we remove one pole at infinity, it means we are removing one element or we are getting one element inductor or a capacitor depending upon whether the function is impedance or admittance. This is the first method. Now the second method is removal of pole at origin. So how will distinguish whether there is a pole at infinity? It means this A0 is 0. The function we have the Bm at s to the power m plus Bm minus 1 s to the power m minus 1 plus B1s plus B0 divided by An s to the power n plus An minus 1 s to the power n minus 1 plus A1s plus A0. When A0 is absent, it means the function has a pole at origin. This is the way we can identify whether the pole at origin is available or not. So A0 must be 0. So this is the function. So how will do the removal of pole at origin? It is very simple. What we do? We just arrange the polynomial in ascending order. Numerator and denominator polynomial both we arrange in ascending order, and then we carry out the division, one division. After one division, what we do? We get this value, this plus remaining this ratio of polynomials. So suppose this Fs is impedance function. If Fs is impedance, then this element is a capacitor. So if you remove one pole at origin, if the function is impedance, we are getting one capacitor or one capacitor element of capacitance 1 by K0. So basically if we look at this is the impedance we write here. So if it is K0 by S, it means C is equal to 1 by K0. Simple way we can get the value of capacitance, which is 1 by K0. If the function is impedance, we get the capacitance or capacitor of capacitance 1 by K0. If the function is admittance, it means we are getting one inductor, and this is the network. So this is removal of one pole, removal of pole at origin. and then the remaining function. Then we check whether there is a 0 or pole or whatever function, then we carry out. If the function is admittance Ys, then this represents a inductor of inductance 1 by K0. So this is the circuit. If the admittance, then we are getting one inductor and remaining function. So removal of pole at origin, if the function is impedance, we get the capacitor. If the function is admittance, we get inductor. Now come to the third technique, which is removal of conjugate imaginary poles. So this is the function having one conjugate imaginary poles plus minus J1. So after carrying out partial fraction, so we can write here, if you remember, this is K1 upon S plus J omega 1 plus K1 star S minus J omega 1 plus remaining function, whether it is pole or J. So if you carry out the exercise of this portion, we get this twice K1 upon S square plus omega 1 square. If we add it, we get this plus remaining F2S. This is F2S. F2S we can write, okay. So this is, we get this 2 K1 upon J omega 1 plus K1 star upon S minus J omega 1, we get this. So suppose if the function is impedance function, so what does it mean 2 K1S upon S square plus omega square? What does it mean? It means this is LC tank. So we take the admittance of this, so SL and 1 by SC. So this is basically, if we take in the S domain, so it is 1 SL and this is 1 by SC. So SL into 1 by SC, SL plus 1 by SC, we are getting this. So this is the impedance of a LC tank, and what we do, we carry out the comparison of this. So twice K1S is equal to 1 by CS, so C is equal to 1 by 2K1. So this way we can get the value of this capacitor, this, and 1 by LC is omega 1 square so L is equal to 1 by C omega square. So this way we can get the value of L and C. So C is 1 by 2K1. So basically it is 2K1 upon omega 1 square. So this is the value of the inductor, which is 2K1 upon omega 1 square, and capacitor is 1 by 2K1, and we can get the value of K1 and omega 1 from the function. From the given function we can get the, after carrying out the partial fraction expansion and carrying out the heavy side expansion theorem to get the coefficient K1, we can get the L1 and C1. So this we have explained. So this is if you remove one imaginary poles, we getting one LC tank. L and C, they are in parallel and all the elements are in series. So this element we can get. So this we are getting by removing conjugate imaginary poles. Okay. So this method. Suppose if the function is admittance, so if the function is admittance, so this L or L1 and C1 they will be in the series and remaining with parallel with remaining elements. So if the function is admittance, so this is, so we can get the value of this inductor and capacitor. So what is Zs is equal to this much, so Zs is this, so Ys is this, and comparing we can get 1 by L. So 1 by L is equal to twice K1. So L is equal to 1 by 2 K1 or L1 is 1 by 2 K1 and omega 1 square is 1 by LC. So we can get C. So C is 2 K1 upon omega 1 square and the circuit is like this. So and circuit is like this. So this is the, if the function is admittance, so L and C they are connected in series and in parallel with remaining element of the network or circuit. So what we have learned, we have seen that if you remove one imaginary poles at conjugate imaginary poles, we get one LC time. If the function is impedance, this L and C they are in parallel in series with the remaining circuit elements. If the function is admittance, so this L or C they are in series and in parallel with remaining elements of the network. Now come to the removal of a constant. So what we do in this, we just, it has a minimum value K mean at some frequency, and since this remains greater than or equal to 0 for all values of omega, so it is feasible to extract a constant K which is less than or equal to K mean without affecting the positive realness property of the function, and this real part of the j omega must be greater than or equal to 0. This must be real part of j omega should be greater than or equal to 0. Okay, so this way we can carry out the synthesis. So there are 4 methods: removal of pole at infinity, removal of pole at origin, removal of conjugate imaginary poles, and removal of constants. So these four methods or their combinations we can use to decompose a function to get the required network. We can carry out some examples. Suppose this function is given. So we can see that s square plus 2s plus 6. So A0 is 0, A0 0. So this Zs has a pole at origin. So this can be written as plus 2s plus 6 upon s into s plus 3. S pole at, so poles at s is equal to 0 and s is equal to minus 3. So there is a pole at origin in this function, okay, and this function is a impedance function. So if we remove this pole, we get one capacitor, okay. Removal the pole at origin, if the function is impedance, we get one capacitor. So this, so how will you remove it? Arrange the function in ascending order, both numerator and denominator, and divide the numerator polynomial by the denominator. So after division we get this. So basically it is this function is 2 by s plus s square, 2 by s plus s square plus 3s, okay. So this is basically impedance. So this is also impedance Z1s and this is your Z2s, okay. Now look at here, Z2s is Z2s is s square upon s square plus 3s. So it can be written as y2s, just simplify it, s square plus 3s upon s square. So it is 1 plus 3y(s). So this is y3 plus y4 s. So this is admittance, so this is conductance, and this is also a, what is this? This is inductor of inductance 1 by 3. So here we can see that, so this is impedance, this is Z2, so Z2 is this one, so Y2 is 1 plus 1 by 3. So this is conductor and this is the inductor. So whole network is 1/2 farad. From here this is the impedance, so impedance, capacity impedance of capacitance half, then this is the conductor of 1 mho and this is the inductor of 1 by 3 Henry. So this way we can get the required network or circuit by decomposing the given network function using any of the 4 methods. So in some network, in some functions, what we'll do, we just take the combination of these four methods. So in the next class, we will carry out the synthesis of one element type, one port network, basically 2 elements type, and this is there are the special forms, Foster forms and core forms. In Foster form, what we do the series network realization. This is series network realization. Network realization. This is parallel network realization, means all the elements in this are connected in series. In Foster second, all the elements are connected in parallel. Where in core form, there are 2 core. First is continued fraction expansion about infinity. So here what we do, we remove pole at infinity. Here cosecant continued fraction expansion about origin, removal of pole at origin. So basically in Foster form, what we do, we carry out the partial fraction expansion. So technique is partial fraction expansion. Partial fraction expansion. Here continued fraction expansion about pole at infinity. So in the core first we have to remove pole at infinity. How will do? We just arrange the function in descending order and divide the numerator polynomial by the denominator polynomial. In continued fraction expansion about origin, we remove pole at origin. How will do it? We arrange the given function in ascending order and divide the numerator polynomial by the denominator polynomial. We get the cosecant. So these are some special types of synthesis. So in the next class we will take the 2 elements type. In BTech course it is LC, or you can say the RL or RC networks. So basically it is 2 elements type synthesis of one port network. So how will what is the standard format of your Foster first? The Foster first is like this. Foster first is like this. If this is your one inductor, then we have this, then then so this is the Foster first. Foster first. Foster second is like this. Foster second is then so parallel network realization. So all the elements are connected in parallel. Here all the elements are connected in series. So this sorry, this is the inductor. So this is we can write it, this is capacitor. Okay, capacitor, inductor. So if the function is impedance, we go for the Foster first. If the function is admittance, we go for the Foster second. So this way we can carry out the synthesis. So in the next class we discuss about the Foster first and Foster forms and core forms of network synthesis using these 4 methods. So I stop here, and in the next class we will discuss this. So thank you very much. Jai Hind.